Hello wonderful person, this is Anton, and in this video we're going to be discussing this relatively interesting study that essentially tries to figure out the age of the universe in a completely new way that has never been done before. And in this case, once again, this actually presents us with some very important evidence that we seem to understand the universe pretty well. And so today we're going to discuss this study by Indra Nobanek and the team you see here that try to tackle the fundamental question in science: how old is everything? And specifically, how old is the universe? Because here, knowing the age of the universe is not just a matter of curiosity, it's a vital piece of puzzle in order to help us understand how the cosmos evolved and what its ultimate fate might be as well. But for a very long time, the answer to this question mostly came from two separate methods, and these two methods generally seem to produce slightly different results, which eventually led to the modern crisis referred to as the Hubble tension. And so in this new massive study by scientists from University of Portsmouth, we now have an independent way of verifying the overall age of everything, and basically establishing if our understanding of the universe is correct or if there is some kind of an error after all. And the way it's done is actually really brilliant. It's by using Milky Way's oldest residents. Or, in other words, by looking at various stars and stellar fossils, mostly focusing on the stars in the galactic backyard. Here, researchers were able to provide a powerful independent analysis, basically confirming everything scientists have believed for several decades. The universe seems to be approximately 13.8 billion years old. But in order to understand why this is important, let's first take a look at how this was done before and discuss the two previous methods that were used by scientists in the past. And while the first method looks at the very early universe by studying the famous cosmic microwave background, the CMB. Essentially the earliest light in the universe, representing the afterglow from when the universe became cold enough to finally allow light to escape. In some sense, you can also think of this light as the afterglow of the Big Bang itself. And so here, using the standard model of cosmology known as lambda CDM, and by using data from the Planck telescope, scientists have established that, based on these observations, the universe is once again approximately 13.8 billion years old, or at least that's the age of this ancient light. And we know this because of its redshift. When the universe cooled down, the light was approximately 3000 Kelvin, but today it's about 2.75 Kelvin. And so as the universe expanded and cooled down, this ancient hot universe cooled down from 3000 down to 2.7 degrees. And based on the ideas involving expansion of the universe, researchers calculated that this took approximately 13.8 billion years, give or take a few million years. But the second method is a little bit different. Here it uses what's known as a distance ladder. And so in other words, by measuring the distance and velocity of various objects in the nearby and also late-stage universe, mostly focusing on the type of stars that tend to blink in a very predictable manner, referred to as Cepheid variables, but by also measuring supernova explosions, which we know produce certain types of luminosity, here scientists can figure out the expansion and the distance again, with most analysis suggesting that the universe is at least 12.5 billion years old. But intriguingly, by measuring distances this way, this method consistently gives us a slightly younger age, or basically gives us a slightly higher expansion rate. So according to this method, the universe is between 12.5 and 12.9 billion years old. In other words, there's at least 9% difference. And that's the essence of this Hubble tension. But if the universe is actually only 12.9 billion years old, then any star that's older than this should not exist and should not be possible. Yet, as we've discussed in some of the much older videos, we actually have found stars, such as the famous Methuselah star, which appear to be at least 13 billion years old. In other words, for the most part, we have found stars somewhere out there that at least appear to be a little bit older. Which essentially brings us to this new study that tries to possibly discover a new method in order to find out which method is correct and how old the universe possibly is. And here this new method uses what's known as galactic archaeology. And so just as a geologist would use layers of rock in order to study Earth's history, astronomers can also use fossils in the galaxy itself, its oldest stars in this case, in order to figure out how everything evolved and how old everything is. And by the way, here's actually a really cool picture that you might have not seen before, representing the oldest image of the Milky Way galaxy ever produced. This was created by the William Herschel back in 1785, who tried to create the shape of the Milky Way, trying to deduce the overall star count and assuming that the Sun was somewhere in the middle. But since then we've learned that this was a huge underestimate. And that's because even in this study, researchers used over 247,000 stars in order to find the overall age of the Milky Way galaxy. And these stars were observed using two major tools. First, high-resolution spectroscopy from the Lamos telescope in China, but also precise distance measurements from telescopes like Gaia by European Space Agency. And specifically, the team wanted to focus on subgiant stars. Basically, stars that have just finished the main part of their lives and are starting to change rapidly as they're about to transition into something else. And because their physical properties shift quite rapidly, here it becomes much easier for astronomers to calculate their actual age. But when you're trying to find something as the age of the universe, you have to be quite precise with your data and also have to be very strict with your analysis. And so here the team didn't just take these 247,000 stars, but instead they applied a series of quality cuts to remove stars with unreliable measurements. For example, for all truly ancient stars, they required them to contain extremely low metallicity, or basically mostly be made out of hydrogen and helium, and also be extremely alpha enriched, or containing very high amounts of alpha process elements like oxygen, magnesium, silicon, calcium, and titanium. And in astronomy, by having low metals and being alpha enriched, we know that these very first stars were extremely likely to be born without these heavier elements that would result from various supernovae. And so a star that basically appears to be old, but is then discovered to be full of iron, would essentially be seen as some kind of a measurement error and not truly be ancient. We expect ancient stars to be pristine and contain only simple elements. And so once all of these filters were applied, they were then left with a final, much more accurate sample of 155,600 stars within a distance of about 16,000 light-years from planet Earth, which technically represents just a small part of the galaxy, because the entire galaxy is approximately 100,000 light-years across, but this was a good enough sample to establish the overall age. And well, what followed after this was a statistical analysis. Specifically what's known as a Markov chain Monte Carlo method. Although, as a side note, in case you're actually wondering exactly how they found the age of each star, here they used a very specific stellar evolutionary model referred to as the YY isochrones, or Yonsei-Yale isochrones, which represents a kind of a stellar grid that's very often used in astronomy to determine the age, the mass, and the metallicity of various star clusters and stellar populations. This is actually the newest model we have from back in 2013, and it focuses on analyzing chemical composition of various stars and star clusters in order to then put them on a graph where their age can be estimated. You can find exactly how this is done in one of the links in the description. And so here, by measuring how bright and how hot the star is, and by seeing the elements inside of it, it becomes possible to determine its overall age. And then by comparing different types of stars and putting all of them on the same graph, you eventually get something that looks like this. And so here it becomes possible to get a relatively accurate age measurement for any kind of a subgiant star. And so by using this relatively large sample in the Milky Way galaxy, the team discovered that the oldest star seems to be approximately 13.73 billion years old, or essentially almost 13.8 billion years old, as we've previously discussed. And while we know that stars very likely did not form right after the Big Bang, with most models basically supporting the idea that they took at least a few million years, with maybe as much as 200 million years. This is actually based on some of the observations from the James Webb Space Telescope. And so if you add that to the age of the oldest star, you essentially get the total age of the universe of approximately 13.9 billion years old, with this result being remarkably consistent with the prediction from the CMB, but very different from the prediction using the cosmic ladder method, which also of course matches previous studies of individual stars like the Methuselah star and various ancient globular clusters, which also have the estimated age between 13.6 and 13.7 billion years. But I guess the question is, okay, so what exactly does this mean and what does this show us? Well, first, once again, this is a major win for the modern cosmology, specifically the lambda CDM model. Here, by using a completely independent method, and by using a method that involves the evolution of stars, researchers managed to come up with an extremely similar estimate by just looking at the age of our own galaxy, independent of the age of the universe. Second, and I guess more importantly, this casts serious doubts on certain solutions in regards to that previously mentioned Hubble tension, because some theories try to fix this tension by introducing new physics, or by suggesting that maybe the universe changed its rate of expansion, and even suggesting that the universe might be almost 30 billion years old, or, in contrast, much younger, with the acceleration of the universe changing over time. And so quite a few of these solutions predicted the universe to be of different age. But if you have the universe that's 12.9 billion years old, for example, it's not going to contain stars that are 13.7 billion years old. And many of these stars have been discovered right here in the Milky Way galaxy, definitively showing us that the universe has to be older. And so these ancient stellar fossils suggest that whatever is causing the Hubble tension and whatever is causing this cosmological mystery is most likely some kind of a late-time phenomenon. Or in other words, it's something that most likely just started happening relatively recently, in the last few billions of years, or is something that's extremely localized and is basically specific to the local region of space. So maybe this is just something that's happening within approximately a billion light years away from the Milky Way and is not something that's universal everywhere. As a matter of fact, it's quite possible that this tension is not even the result of new physics at all, but could be caused by the fact that we're just inside this extremely large void of low-density space, which is potentially making the local expansion look much faster than it truly is. In other words, this could just be observational bias. But despite this intriguing study and these somewhat intriguing results, we obviously still have to be cautious, with researchers mentioning that there are still 5 main sources of uncertainty that could affect these numbers. In this case, the sample size, the quality of data, and even the computer models for stellar evolution could have all affected the results. And so basically there are still certain factors that could have limited the precision by approximately 150 to 200 million years. But to get better answers and more accurate results, researchers are already planning part 2. So basically by using subsequent data releases from Gaia and LAMOST, which might help us identify, for example, binary stars that could be faking an older age, all of this will help refine the calculations and eventually get a much more accurate final result. So basically here, by discovering the most ancient star in a galaxy, it will help us discover the most accurate age of the galaxy itself, and thus help us discover the age of the universe. And so in this case, this study is actually a really good example that we don't really have to look far or use very expensive telescopes like the James Webb in order to understand the entire universe, and specifically in order to figure out when the universe began. And so sometimes some of the most profound answers can be found by looking at the oldest residents in our own neighborhood. And the fact that some of these stars seem to be just as old as predicted by the cosmological models seems to definitely strengthen the case that the universe is indeed approximately 13.8 billion years old. But once we get additional data, or once something else is discovered, we'll come back and discuss this more in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon, where you can find additional videos without any ads, and can DM it directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.